This video is a supplement to what I do in lecture, but it does serve as both a review and a preview of what we did. I'll always draw the ray tracing process in detail in class so you can see how it works. It's a graphical alternative to the actual equations, whose main virtue is it shows you how images form and the difference between real and virtual images. However, it will give you the exact correct results if you do it very carefully, respecting the geometrical rules that underlie the equations that we use in numerical calculations. I've drawn these on top of the textbook diagram so they get a bit busy. I've done this so that you can see the difference between what is a careful calculation and what the artist provided in the textbook. First, a concave mirror where the focal length is positive. The first ray I draw I call ray 0. That's the central ray and the easiest one to draw because you just connect a single line between the object and the center of curvature of the mirror. So you just lay a straight edge across the center point at twice f and the object, draw a line there. The thin arrow with the arrow on the end is what we want to emphasize because it shows where the ray goes when we look at it. The primary ray I call ray 1 because it is the first primary ray. It respects what happens with this kind of mirror, which it converts a parallel ray into a ray that converges to the focal point. You do it by drawing a ray parallel to the optic axis and then connect the point where it hits the mirror to the focal point. However, you can't actually bounce it off the mirror. The point you have to use is the point where that ray touches a line that's tangent to the center of the mirror, as I've shown in this picture here. If you do anything else, you'll get what's called spherical aberration in your calculation. The secondary ray is one that goes to the focus and then out parallel. It's the reverse of the primary ray. You first connect the object and the focal point, then when it hits the mirror, it comes out parallel. So this is a ray that you go from the object to the focal point, as you see here with the thick line, and then when it hits the mirror, that is, actually hits that green dashed line, it then comes out parallel. This ray, ray 2, is the same as the textbook ray number 2. For a convex mirror, where the focal length is negative, several of these functions are reversed from what they are in the concave mirror. Ray 0 is the same, and that's why I always draw it first. It's always the same no matter what kind of mirror you've got, or for that matter, what kind of lens you got. So you draw a line that connects the top of the object with the center of curvature of the spherical mirror and emphasize the arrow that's going out that after the ray bounces off the mirror. Notice, in this case, I've used arrows and solid lines to show the path taken by the actual photons of light. Dashed lines are always used to extend those rays back into the area where light does not go, where our minds have created an illusion that that's where the ray came from. The big difference, however, is that what was called the focal point is now the unfocal point. That is, parallel rays will diverge from the unfocal point. Ray 1, the primary ray, is parallel from the unfocus. Instead of parallel to the focus, it goes parallel from the unfocal point. So you start the same, but after it hits the mirror, it bounces away from the unfocal point, which is now on the negative or virtual side of the mirror. So as you can see here, it goes not to the mirror, but to that same tangent plane that correctly takes care of the geometrical argument to locate the image. This is ray 1, same as textbook ray number 1. The secondary ray, what I call ray 2, of course, is a ray that comes out parallel after using the unfocal point. The light goes towards the unfocus and bounces out parallel. So you draw a line that connects the object and the focal point and then construct a ray that comes out parallel. So again, this heavy line goes towards the unfocal point and then bounces out parallel, and a dashed line shows your reconstruction of where that ray came from. This ray is the same as the textbook ray number 2. Now, when you do it the way the textbook draws it, you introduce some errors, some spherical aberration. As I've pointed out, the rays, when you do the correct geometrical construction, have to reflect off of the dashed line tangent to the mirror, not from the surface of the mirror. This is the only way you can get the ray diagram to be a geometrical solution to the equations for the paraxial approximation that we use. If you don't do this, like is done in the textbook, your drawings will all suffer from spherical aberration, as I'll show in these cases from the textbook. The heavy blue line is the central ray. Notice that it does not cross the other two rays at the point where the image is shown to be. And in fact, that image is not in the correct place. The object is a little bit less than 3 times the focal length, so the image should actually be a little bit past 3/2 of the focal length, and it's not. 3/2 of the focal point is at the end of that little pink arrow you see in the picture, and you can see the image is actually inside of it instead of outside of it as it should be. So the image is not where it should be, and the central ray does not intersect the other two rays. And the reason is the spherical aberration due to using the mirror rather than the tangent plane. If we shift over to using the tangent plane, as I've done here, notice that little yellow highlight of the point used for the parallel to focus ray. That shifts the intersection point of the two primary and secondary rays that were shown in the textbook out to where they intersect with the central ray as they should, and it moves the image out a little bit further so it's a little bit past the 3f/2 point, again, where it would be if you calculate it from the numerical values for the location of the object. So when the geometrical construction is done right, the image is in the right place. Now in this case the errors aren't very big, and that's because the image itself is small. When the image is enlarged, magnified, the errors are also enlarged. So for example, in this case, where the object is about halfway between the center and the focal point, the image should be at 3 times the focal point at the end of that pink arrow where I've drawn a teal image arrow. And you can see that the actual image is nowhere near that. Similarly, the central ray from the object to the center of curvature of the mirror is nowhere near the intersection point of the primary and secondary rays shown in the textbook. The image is not where it should be, and the central ray is not even close because of the spherical aberration that results from the way in which the drawings were made. If we bounce those rays off of the tangent plane at the yellow highlighted points, then that shifts the intersection point of the primary and secondary rays, so they agree with each other and with the central ray, and that moves the image way out, as you see, to about 3f, where it should be. The image is where it should be, and all 3 rays cross there. Now, for this virtual image case, the situation is also quite bad. The object is about 0.6f. I scaled that off of the drawing. In that case, the image should be about -1.5f, which is where that teal arrow is at the end of the pink arrow. Very large distance away from the image shown in the textbook. So the image is completely wrong, although it happens that the central ray intersects the other two. The spherical aberration actually affects all 3 of the rays. If I go to the correct intersection point, as you see in this drawing, that is, if I go to a point where the bounces off of the green dashed line, I now get a much taller image. It's much further away, and all 3 rays cross at the same point, which is about where it should be. That is, for the object at about 0.6f, I should get an image about -1.5f, which is where that green, sort of teal green arrow is located. So these examples are all taken from chapter 31 of our textbook, although a number of these pictures have been modified to clean them up to make them easier to use for my purposes in this video.